open all the time.
Hello everyone and welcome. Today we are going to deep dive into the back-end architecture of a high-performance real-time messaging application. When you need to send a message on WhatsApp or a Messenger, you expect it to arrive on the other person's screens instantly. Achieving that seamless experience at scale requires a decoupled, fault-tolerant back-end. In this presentation, we will bypass the front-end user interface and look exclusively at the internal workings of the system. We'll explore how we integrated WebSockets for real-time bidirectional communication, Apache Kafka for event streaming, and MySQL for persistent storage. So, to understand our architecture, let's look at our four core pillars of our backend. First, we have our Rocket WebSocket server. This is a persistent PHP process running on an event loop. It holds thousands of open, active connections to our users without timing out. Second is we have our Kafka Apache. Kafka acts as our message broker and event streaming platform instead of our WebSocket server. Trying to do database operations while serving clients, it simply drops an event into Kafka and moves on. Fourth is we have our background consumer script. This is an independent, long-running PHP process that listens to Kafka. It does the heavy lifting, processing data, writing to the database, and triggering notifications. And finally, our persistent storage is managed by a MySQL database utilizing optimized query statements to track message history and status like sent, delivered, and seen. So, what exactly happens when a user press send or sent a message? Let's follow a single message through our system. So, step 1. Step 1. If a user sends a message, then we could see it the WebSocket server receives the message. Instead of locking it up in the server to execute a database query, it acts as a Kafka producer. It packages the sender ID, receiver ID, and text into an event and publishes it to the chat message Kafka topic. The server immediately returns to listening for others users. So, let's see it here. Almost instantly, our Kafka consumer pulling the central broker sees the new event. It plucks the message off the queue. The consumer processes the payload and securely inserts the message into record into the MySQL database using prepared statement. With the message safely stored and consumed, makes local HTTP requests back to a hidden push API running on the WebSocket servers. It says, "Hey, I just received a message for user B. Here's the data. Then the WebSocket server checks its active memory. If user B is currently online, it pushes the message down to user B's active WebSocket connection in real time. So now let's take a look closer at how it is implemented. Server-side logic and connection mapping. In our chat server class, we maintain a SQL object storage map. These structured maps actually leave network sockets to our database users' IDs. When a client authenticates via WebSocket, we immediately loop through all other active sockets and broadcast a presence event. This tells everyone's client that a new user just came online. So, when in data processing and event streaming, the on message event triggers, it critical we don't block the React PHP event loop. We utilize the long PHP Kafka library. We serialize incoming chat text into lightweight JSON package and fire it into the Kafka cluster with set acknowledge to -1 to ensure data reliability without bottlenecking the connection layer. And for the database interaction, our chat uses our chat consumption.php script is our data processor. It runs an infinite loop using Kafka consumer interface. Because it runs independently of web server, it can safely take the time needed to format the MySQL insert statement, bind parameters to prevent SQL injection, and extract the resulting database to insert ID. Real-time communication bridging. The final implementation of the puzzle is getting the message back to the socket layer after it's saved. To solve this, our WebSocket script spins up a second socket under the same React PHP event loop. An HTTP server on port 8083. The consumer sends an internal push request to this endpoint because both the HTTP endpoint and the WebSocket share the same memory space. The HTTP endpoint can directly command the WebSocket array to send the final payload to user B's browser. So, what have we learned in this video? So number one, the power of persistent connection. We learned that traditional HTTP requests are often too slow for modern chat. By utilizing WebSocket, we were able to keep a constant open connection between the client and the server. This allows us to push updates like new messages online and online presence instantly without forcing the browser to constantly refresh or pull the server. And number two, the importance of the coupling system. Early on, we realized that if our WebSocket server had to pause and write every single message directly into MySQL database, it would create a massive bottleneck by introducing a message broker like Kafka or RabbitMQ. We successfully separated our fast, real-time messaging deliveries from the slower, heavier task of database storage. The broker handles the heavy lifting in the background, keeping the chat snappy for the users. And number three, assembling a polyglot architecture. Finally, we learned how to make entirely different technologies talk each other seamlessly. We brought together PHP backend, a MySQL database, a custom WebSocket server, and an event broker. tying them all together with asynchronous consumer scripts and an internal HTTP APIs. In the end, this project proves that building a real-time system isn't just about the code. You're right, it's about choosing the right architecture that can handle speed, reliability, and future scale. So that's it. Thank you for watching. Goodbye.